Hello and welcome. In this video, we are going to talk about the Z-test, one of the first tests that you would learn about in the process of hypothesis testing. While this is the first test that we're going to talk about, this would set up the foundation for the rest of the test. So you would get a better understanding of the complete test procedure. First, we're going to qualify which kind of test applies in what kind of scenarios. Second, we are going to look at how to state the null and the alternate hypothesis. Third, we are going to look at the level of significance, which is typically provided in the problem statements. Fourth, we are going to look at the calculation of the test statistic and p-value, which can be done manually to some extent with the help of tables and can also be done using the modern day tools. And then finally, we're going to learn how to conclude the hypothesis test. What was the end result? Now, these steps might vary as you refer to different books and resources, but by and large, the structure remains the same. Before I proceed any further, if this is the first time that you chanced upon a topic like hypothesis testing, my only request would be that you go ahead and watch a previous video that we've created in the sequence. I'm providing its link in the description. Why I'm saying so is because the biggest challenge people face with a topic like hypothesis testing is that they're bombarded with a lot of new terminology. And if you've not really patiently understood what each of these terms mean, for example, what is a null hypothesis, what is an alternate hypothesis, what is a type 1 error, what is a type 2 error, till the time these concepts are not very clear to you, you would not be able to get a good grasp of the subject. Unfortunately, the way these books explain this topic is not very interesting, and that's why a lot of people struggle. So we put a very good effort in explaining this to you in the simplest possible way through this video, for which the link is available in the description. Trust me, it's worth spending that time because it'll definitely save hours of your struggle. But if you're comfortable with these terms, then we can proceed. So as I said, we're going to talk about the idea of Z-test today. Let's first understand when do we perform a one sample Z-test. A one sample Z-test is the right test for us to perform when you are trying to compare the mean of a sample. So we could be given a raw data and we can calculate its mean, or we could be just given the mean as a value in the problem reference, and we are comparing that mean with the hypothesized population mean. One important condition, however, here is that along with the population mean, you should also know the population standard deviation. There are other assumptions as well that we're going to discuss, but it's one of the major assumptions that you know the population standard deviation as well. So you're basically trying to compare two means. One is something that you've collected from a sample. The other is a hypothesized value or a reference that's given to you. What are the major assumptions involved in a one sample Z-test? Number one is that the observations that you've collected are collected randomly. So the sample should be such that its observations are not collected with a bias. When you were collecting those observations, everything had an equal opportunity. Second is these observations are not related to each other. There is an independence. If I pick one value from the population, the next value that I'm going to pick would have no influence of the value chosen earlier. Third assumption here is about the normality of the parent population. So the sample is being collected from a population which is normally distributed. And the last assumption is, as stated earlier, the population standard deviation is assumed to be known. Now, there is a way around this, especially for the last two assumptions. If you're working with a sample size which is greater than or equal to 30, so at least 30 observations, then the assumptions of normality of the parent population and the population standard deviation being known can be bypassed. Normality can be bypassed because when you're dealing with large sample sizes, then as per the central limit theorem, the assumption of normality is assumed to be in place. So it doesn't matter whether the population was normally distributed or not. When you have large sample size, it holds good. Second is, when you're dealing with sample size greater than or equal to 30, the population standard deviation can be approximated with sample standard deviation. So this is where, even if you don't know the entire population and its standard deviation, you can work with the standard deviation of the sample that's given to you. This is a very important point. Let's start by solving a couple of problems, and that's the best way to understand this. So let's look at the first problem. A company wants to determine if their new marketing campaign has led to a significant increase in their online sales compared to their historical performance, which was on an average 140 sales with a standard deviation of 25. So notice what's given to us is basically the population performance. We have historically recorded on an average 140 sales, and the standard deviation is also given. So this is the population mean, and this is the population standard deviation. They collected data for 30 days during the campaign period. So this is a new campaign. They are still experimenting with it. They are collecting some data and they're trying to check if the sample mean, which is 150, is significantly better compared to the population mean. The company claims their sales performance indeed has improved due to the new campaign. Perform a hypothesis test at 5% level of significance to check if the performance has actually improved. Now, if any of these terms, let's say level of significance is something that you're not familiar with, once again, as I requested, watching that earlier video would really help because these topics have been explained quite well there. Let's get started step by step. Is this a case that qualifies for one sample Z-test? So I have a population mean, population standard deviation. The sample size is, again, we have observations of 30 days, which is the borderline case, but 30 or more is a good choice. We have a sample mean available. Now, how do we actually go about solving this in step by step? First thing would be that do we know the level of significance? If you read this line in the problem statement, it states that 5% level of significance is supposed to be checked. What does this 5% level of significance mean? It means that while rejecting the null hypothesis, we don't want to make more than 5% error. So error has to be capped. We don't want to exceed on error. That's not a good performance indicator. Error is something which is bad. We should put a cap on it. We are not allowed to make more than 5% type 1 error. Now, if you look at the hypothesis statement, what is the null hypothesis here? The null hypothesis would be that new sales are at par or worse, you can say. You can write it as less than or equal to compared to the historical sales. But null hypothesis in practice is always checked at equality. That's why I've put an equal to sign here. So the null hypothesis is new sales are just as good as the historical sales. The claim that the company is making is that the new sales have significantly improved compared to the past sales. So hypothesis in general is always triggered with the alternate. Null is something which is the prevalent belief, which is assumed to be true. Alternate is something which challenges the status quo. So if you have reasons to believe that you're doing something different from the common belief, is when you write the alternate hypothesis. In this case, the company's claim is that the new sales have improved compared to the historical sales. Now comes the test statistic. Now, every test, it's not just for Z-test. Any hypothesis test that you're going to perform would always have a test statistic. It would involve some calculations, which nowadays you don't have to do manually because most of the tools have these built in. But if you're a student, you're writing an exam in stats, then they might expect you to know these formulae as well, and you may have to do manual calculations as well. So let's go with that scenario. The test statistic, if you see, is X bar. Now, if I put the labels for each of these, this is what it stands for. So this X bar represents the sample mean. The mu represents the population mean. Mu in general is the way to denote a population mean, and sigma is the general way to denote a standard deviation of the population. N is our sample size. So do we know all these things here? Maybe yes, we just saw these in the problem. Now there are two ways to solve this problem. And we're discussing both, and I'll also tell you what is more relevant in the academic scenarios and what is more relevant in the industry. So the first approach is a critical value method, and the second approach is a p-value method. Let's look at each of these one by one. First of all, understand this problem visually. What we have is a normal distribution. At least we can assume it's a normal distribution. And we are marking a critical value here. How do we get this? This is the borderline for that 5% alpha region. Why did I place the alpha region here? I'll show you other examples where alpha is on the left tail or equally distributed. But right now, why did we place alpha or the level of significance on the right tail? It is because we are solving a greater than kind of problem. You're claiming that the new sales value is greater than the previous sales value. This is the reason we have to put the entire alpha risk on the right tail. The borderline for this alpha region is the critical value. So this shaded region is alpha, and this dotted red line is the critical value. How do we get this value? Of course, we can get it from the table, and I can show you a couple of other ways to get this as well. We can use the formula called norm inverse. We have to mention the probability. Remember that the area under the curve is always calculated from left to right. So when you're looking for the borderline for 5% on the right, you have to mention 0.95 here. The mean is 0, and standard deviation is 1 because we are referring to a standard normal distribution. this comes to 0.1645, which is exactly what you see mentioned here. If you're not familiar with the idea of area under the curve and the normal distribution, then you can definitely watch this video on normal distribution. See, this is a relatively different topic, so it would require a little bit of pre-work. Luckily, the videos in sequence are already available. So you can watch the first video, as I indicated, for hypothesis testing. You can watch the video on normal distribution. It will make more sense. This video covers everything about the area under the curve using the Z table, Microsoft Excel, and even Python. Coming back, we've listed down whatever is given to us in the problem. Sample mean is known, population mean is known, population standard deviation is known, and the sample size is 30. Now we have to plug these values in this formula. And if we do that calculation, we get an answer which is 2.19. What is this? This is the test statistic. Now, visually, what does it mean? Your critical value is this red dotted line, and the test statistic is this green dotted line. So what do we learn from this? If your test statistic falls in the critical region or the alpha region, you can go ahead and reject the null hypothesis. If this test statistic would have fallen to the left of this red dotted line, we would have failed to reject the null hypothesis. We'll see that in a different example. But right now, with the critical value approach, you can say that since the test statistic falls in the rejection region, we can reject the null hypothesis. If you write the statement a little more formally, you would say something like this. Since the test statistic 2.19 falls in the rejection region, that is to the right of the Z critical or the critical value, which is 1.645, at 95% confidence, we have the evidence to reject the null hypothesis. This is the first method, or the critical value method. A lot of places, they still expect you to decide basis the critical value, especially in the academic scenarios. But when it comes to the industry, a more prevalent way, of course, is using the p-value method. And that's not very different because p-value would only talk about the area, the shaded area. So if you see, the area to the right of the red dotted line was a bigger area. Could see this earlier as well. This entire area to the right of this line is a bigger area, whereas area to the right of the test statistic is a smaller area. Now, this shaded region that you see here is actually called the p-value. So we compare the p-value with alpha. If p-value is less than alpha, which means we are still operating in the permissible limit. What is a permissible limit? Well, we are not supposed to exceed in making error beyond this line in order to reject the null hypothesis. But as long as we are operating in this limit, we can reject the null hypothesis. So whether you decide basis the critical value method or the p-value method, which talks about comparing the area under the curve, the p-value is less than alpha or the level of significance. That's why we can reject the null hypothesis. So this is visual representation, but if you want to calculate the p-value and compare in numbers, how do we do that? Let's understand this. Let me take you back to Excel. This time, we will be using a function called normTest. We have to mention the values here. So the value that we are looking for is 2.19. The mean is 0. The standard deviation is 1. And it's always a cumulative calculation. Again, this is something which we have explained at length in the normal distribution tutorial. This value comes to 0.985. Once again, this is not your answer. Why? Because this is always calculating the area from left to right, which means right now you've calculated this area up to this green dotted line from the left up to this point. Whatever area comes under the curve is what you've calculated, but you want this area. So you'll have to just do 1 minus. So we'll have to do 1 minus this area to get this, and the p-value comes to 0.014. Now, of course, you can see that 0.014 is definitely less than 0.05. So we can say p-value is less than alpha, and that's why we can reject the null hypothesis. If you were to write it more formally, it will be something like this. Since the p-value is less than the level of significance alpha at 95% confidence, we have the evidence to reject null hypothesis. So you just now saw that whether you solve the problem using critical value method or p-value method, the end conclusion is going to be the same. In both the cases, we rejected the null hypothesis. Let's move to the next problem statement. We'll cover all possible examples so that beyond this video, you don't have to refer to any other source to understand ZTest. Let's take another problem. Slight change in the language, if you see. A company wants to determine if their new technology upgrade has led to a significant decrease in their warranty claims. Any company that's into producing products would be concerned about the warranty claims. A warranty claim is, of course, a bad experience for the customer. who's claiming that warranty. And of course, it talks volumes about the quality of your product, right? So companies would monitor it closely. Now, the historical warranty claims, if you see, are 200 on an average, which is your population data. They collected data for 50 days, which has a mean of 180 warranty claims with a standard deviation of 120. Now, there is a slight change here. Earlier, you were given the population mean and the population standard deviation. Now we are saying we're giving you sample mean and sample standard deviation. The company claims their warranty claims indeed have reduced due to technology upgrade. Perform a hypothesis test at 5% level of significance to check if warranty claims have actually reduced. Now, since we've understood one test, it becomes easier for us to now follow the subsequent problems and tests. Does it qualify for a Z-test? We've been given a population mean. We've been given a sample mean and a sample standard deviation, and the sample size requirement is satisfied. So that box is checked. Second is, do we know the level of significance? Well, yes, that's stated in the problem, 5% level of significance. Now, it does not have to be 5% all the time. That's more of a norm. If the test that you're performing is extremely critical, you would want to keep it more stringent if the consequences of your test lead to life or death kind of a scenario. So 5% is just an example. You have to read the problem statement every time carefully, then you get to know what's the level of significance. Normally, it is given as 5%. Now, stating both the hypotheses, this time, it's a different scenario. You can say that null hypothesis would hold equality or greater than or equal to sign, but it'll always be checked on equality. That's why I put that sign here. So new warranty claims are at par with the historical warranty claims. There is no improvement due to the technology upgrade. The product quality has not improved. It's one and the same. However, the company is claiming that the warranty claims have reduced compared to the historical warranty claims. If you see, the earlier hypothesis that we talked about was that new sales are greater than the historical sales. Now we are talking about a less than sign. New warranty claims are less than the historical warranty claims. Test statistic remains the same, but there would be a change here. We don't know the sigma anymore. We have to cut this. We have to bring the sample standard deviation S here instead. And then we know everything that we need to put here in this formula. If you plug those values, this is how the calculations would be. The warranty claims new average is 120. Earlier average was 200. Standard deviation is 120. And sample size we've taken is 50. If we do this calculation, this value is approximated to negative 1.18. Let's understand visually how does it look like. So this is the scenario. Now, if you see, we have to put the alpha risk on the left tail because it's a less than kind of alternate hypothesis. If you look at the critical value, it is negative 1.645. And the test statistic is negative 1.18, which is to the right of the critical value. Basically, it doesn't fall in the rejection region here. So from the critical value method, you would say we fail to reject the null hypothesis. We normally don't use the word except for null hypothesis. We don't say we accept null hypothesis. We say we fail to reject. There's nothing called as accept null hypothesis because that's the prevalent belief that's assumed to be true. Since the test statistic does not fall in the critical region, we fail to reject the null hypothesis. And let's look at it through the area under the curve approach also. This is a scenario where the p-value is greater than alpha. So this much region was allowed for rejection. But what we've done is we've gone overboard. So you see this additional purple region here. So the p-value is alpha plus this region, which is obviously greater than the alpha value or 5% region. And that's the reason we fail to reject the null hypothesis. Let me do this calculation for you in Excel. So we're at the second problem, and let's quickly note down the information that has been provided to us. So we can apply the norm dist calculation here. The value that we are checking is negative 1.18 as we compute it. The mean is 0 for a standard normal distribution. The standard deviation is 1, and it will be a cumulative calculation. We got this answer as 0.119. Do we need to do a 1 minus here? Not really, because the area is already calculated from left. So we don't need a greater than area here, and that's why we don't have to do a 1 minus. Now, the value that we calculated is 0.119. Obviously, 0.119 is greater than 0.05, which is our level of significance or alpha. So when the p-value is greater than alpha, we fail to reject the null hypothesis. So we can write, since the test statistic, negative 1.18, doesn't fall in the rejection region, that is to the left of Z critical, which is negative 1.645 at 95% confidence, we fail to reject H naught. Where is this 95% confidence coming from? This is 1 minus alpha. So if your alpha would have been 3%, you would not say 95% confidence, you'll say 97% confidence. Likewise, if your alpha was 10%, you will say 90% confidence. Confidence level is nothing but 1 minus alpha. All right, so let's move to the next example, which is a two-tail test. We have performed a right tail test, we performed a left tail test, and now we are talking about a two-tail test. Slight change in the language. A company wants to determine if due to the maintenance cost cuts, their customer complaints have changed compared to their historical complaints, which was on an average 100 complaints with a standard deviation of 20. What is this? The historical data that's been given to you for a lifetime would be the population data. And they perform some cost cuts, after which generally you would expect a change. But there is no claim related to whether the complaints have gone up or gone down. It simply talks about whether we have changed. So you can't say a greater than or less than. You have a not equal to scenario in the alternate hypothesis. We'll check that very soon. They collected the data for 36 days. The sample size is greater than 30, which has a mean of 105 complaints. Perform hypothesis test at 5% level of significance to check if the complaints have actually changed. Once again, we can be a little fast this time because we understand the basic structure of how you approach these problems. 5% level of significance is something that's very clear to us. This is a not equal to hypothesis. Like I said, null hypothesis will always be checked at equality, or it will complement the alternate hypothesis, but we can always include equality here. But the alternate hypothesis would not involve equality. It is talking about a not equal to scenario, not a greater than, not a less than scenario. Test statistic remains the same. So we will do the calculations, plugging in all the values. 105 is your sample average, 100 is your historical average, 20 is your population standard deviation. You have 36 samples. If you do this calculation, you'll get the Z value 1.5. Now, how does this look like visually? Notice that in this case, you have to divide your alpha risk in two equal parts, because we were not categorical in mentioning it in the alternate hypothesis that it's a greater than scenario when you put entire alpha risk of 5% on the right tail, or nor did we say that the risk is entirely on the left tail through a less than scenario. So what we simply said is that we are claiming that this is not equal. When it is not equal, it could be both greater or less. We are dividing it equally. So this is 0.025 or 2.5% area, and this is again equal 2.5% area. Obviously, you know the shaded region is the rejection region. And where is our test statistic falling? This green dotted line is, of course, not in the rejection region. So in this case, again, you will not be able to reject the null hypothesis. The p-value approach would require you to calculate the p-value, and you can compare that p-value with an alpha by 2. Or a 2.5% region. Let me quickly do this in Excel. So we can use the norm dist again here. The value that we calculated was 1.5. The mean would be 0 for standard normal distribution. Standard deviation would be 1. And we are doing a cumulative calculation again. So this is going to be 0.933. But is this the answer? Not really. In this case, once again, if you see, this is calculated the area from left up to this point where you have this green dotted line. What you need is the area to the right of it. So what we can do is we can do a 1 minus of this, which comes to 0.066, which of course is greater than 0.05. But in this case, you would be comparing it with alpha by 2 or 0.025, because this is a two-tail test. Of course, 0.06 is greater than 0.025. So once again, the p-value is greater than alpha, which means we fail to reject the null hypothesis. Now, I'm aware that some of you are data science students and you'd want to see how these things work in Python. So for you, we have a library called SciPy, from where we need the class called stats. This has all the functions that we need. First of all, we have to do the same calculation as we did earlier. These are the values that we are looking at. So 150 minus 140. 150 is the sample mean, 140 is the population mean. This is the population standard deviation. This is the sample size. We are taking a square root of it. These two asterisks followed by 0.5 means raised to the power 1 by 2. So this is the same formula, and the calculation is 2.19. We saw that earlier as well, 2.19. So coming back, if we know this, all we have to do is we have to use a formula, which is the same as the norm dist in Excel. You have to do stats.norm.cdf, put this value, mean is 0, standard deviation is 1, and you get the probability at 0.014, which is exactly what you got when you used the norm dist. The sample mean is 180, the population mean is 200. The sample standard deviation, we've approximated to sample standard deviation that's given to us as 120, and the sample size is 50. again raised to the power half or square root, you get this approximated to 1.18, negative 1.18. That's what you got here. And now we just have to convert this to the probability. So if we use stats norm CDF, negative 1.18, notice we are not doing any 1 minus in this particular case because this is already on the left tail. And this value comes to 0.119. Let me show you what we got in Excel. Here is the value that we calculated in Excel, 0.119. The sample mean is 105. The population mean is 100. Population standard deviation is 20. Sample size is 36. We've taken a square root. This computes to 1.5. And if you plug it to the formula, once again, we'll have to do a 1 minus in this case if we're calculating the area to the right. So we calculated the area and we've done 1 minus to get the area to the right. And then we are comparing it with the right tail, which is only 0.025. Of course, you can see this is 0.06, as you could see here. So all the answers exactly match. All right, so with this, we come to an end of this video. I hope if you followed along entirely, this video would have made sense and would potentially iron out all your queries related to the hypothesis testing. This video would serve as a baseline to a lot of stuff that you're going to learn in the subsequent videos on hypothesis testing. So if you get this right, the journey is going to be a lot smoother because there's a step-by-step logical procedure, and we're going to give you complete clarity on that.